So good afternoon, gentlemen. It is a pleasure for me to welcome here Jan Valášek from the Czech Technical University, from the Faculty of Mechanical Engineering, Department of Technical Mathematics. Jan Valášek obtained his master and PhD degrees at the Czech Technical University, and at present he works at the Department of Technical Mathematics as a postdoctoral researcher, and he has been interested for a long time in human voice and in numerical simulations of fluid structure interaction and fluid structure acoustic interaction by the finite element method with applications in human phonation. And so he will speak today also on this topic. The title is Numerical Modeling of Human Phonation Process, and we are looking forward to your talk. Please.
So thank you very much for your introduction and also for possibilities to speak on this seminar. I a little bit apologize because I will present a rather engineering point of view than completely the mathematical problem. So in this research I also cooperate with my supervisor from the same department. Oh, sorry, I have to learn with this. Valášek from the Czech Technical University, and we have also some experimental cooperation with Institute of Thermomechanics, where they have some experimental laboratory and measurements. And at the recent time, we also received an international project together with the colleagues from the Graz University, Professor Kaltenbacher and Professor Deringer from the Erlangen University, where we would like to together really focus on, as well as experiments, numerical simulation, and finally also the acoustic simulation. Yeah. So what is our motivation for this mathematical modeling? This basically how the human voice is produced. So first, you can see here at your neck there are vocal folds, which under the pressure of incoming stream from lungs starts to vibrate, and by this vibration they really change the shape of the domain, and also vice versa influence the whole fluid flow. And we speak about the fluid structure interaction in this sense. Let me show in this moment a small video how it
allows us to look at the vocal cords while they're vibrating and find ways to help them move normally.
Here we can see
your vocal cords move normally, you have the voice.
You can see here the motion of vocal folds, and that the both vocal folds really touch each other, and how they vibrate. This is under the stroboscopy, so the motion is very slow. Okay, and yes, then there are such a noise. So that's something I would like to also address in the end of my presentation. But there is not, as we are interested in the voice, then the basic sound of this voice is produced at the near the vocal folds and close to the most sources, just close behind these vocal folds, and then they are further propagated through the whole neck and mouth, and then they are articulated in real speech by mouth, teeth, and tooth. Yeah, and as these sound sources needs to propagate through the neck, then the basic sound which is produced at approximately at this location is further amplified by the resonant frequencies of your, so which really creates further problems. Look back on the acoustic sources, you can distinguish between the sound sources really created just purely by vibration of elastic bodies, your vocal folds, and more complex ones which are induced due to some unsteady fluid flow motion, which can be in general called like the aerodynamic aeroacoustic sound sources. And this is for the normal human speech is assume that these are the major sound sources, and then we will try to really investigate this more in the second half. So from the numerical point of view or modeling point of view, we in the end end up with such a scheme where we have a classical fluid structure interaction problem, but based on the fluid flow, then we can also get some aeroacoustic sound sources, and they propagate like the acoustic pressure, waves of the acoustic pressure through the neck. And I also speak about vibroacoustic sound sources. And these pressure waves, in general, can further influence the vibration of the vocal folds itself, and then this problem can be in general described like the fluid structure acoustic interaction problem. However, we will simplify the situation, and we will look just for the for the simulation of normal speech when this acoustic pressure is of many magnitudes lower than the common pressure induced by the fluid flow around the vocal folds, and then we can neglect the influence of the acoustic pressure on the structure vibration. And in this setting, it is enough to solve first the fluid structure interaction problem, and then based on the solution, solve the aeroacoustic problem. And the similar we can do also with the vibroacoustic, at least that for speech, normal speech, and not too loud. Okay, so let me look at the mathematical model for the fluid structure interaction problem. So basically, we describe the deformation of elastic body by this partial differential equation for unknown displacement 2. And here tau ij is Cauchy stress tensor. So in this model, we use linear elasticity one, where the Cauchy stress tensor is related to the displacement by the generalized Hooke law. Okay. What boundary conditions we add to this model? So we either prescribe here a zero Dirichlet boundary condition for the bottom of the vocal folds, which should be fixed here, and another part of this elastic body is this common interface with the fluid, and here we prescribe aerodynamic forces, and potentially we can also add here acoustic forces if we really would like to fully couple the whole scheme. Then the forces from the acoustic will be here. Okay. Much more complicated for the description is the part concerning the fluid flow, because we have to deal with the time deformation in time of this computational domain, and therefore we use arbitrary Lagrangian Eulerian method. So I hope you all know this, but basically we have to construct or find some diffeomorphism between the reference domain and the computational domain at time t, where all these boundaries remains fixed with only exception of the interface where we need to map this the reference domain to this one then with the change position of the interface. Once we have this AD map, so-called AD mapping, then we can also compute or define a domain deformation velocity, which is just the time derivative of this mapping, and based on this, we can further define AD derivative of the function with respect to some point in the reference domain according to this formula. So we find that the AD mapping is actually equal to time derivative of the some general function f plus some convective term here in this formula. So then if we apply this formula or transform the whole problem in the time-dependent domain, then we end up with the Navier-Stokes equation in AD formulation, and they look like this. So we have here this AD derivative, then the classical convective term is modified by this additional domain deformation velocity, and there is a viscous term, pressure term, and potentially some additional force term, but we usually put here 0, and we assume that the flow motion is actually the velocities are so small usually that the incompressible model is a good approximation of this in this fluid structure interaction problem. So we apply here also the divergence equals 0. Okay, in this problem we have more boundary conditions. So basically we have here again 0 Dirichlet boundary conditions at where the boundaries representing walls. We have at the interface we have to somehow prescribe the continuity at velocities, and at the outlet there is a usually prescribed do nothing boundary conditions with 0 on here on the right hand side, but we use a directional do nothing boundary condition where on the right hand side is added some nonlinear term which further increase the stability of the scheme, especially for the case when we have strong vortices going outside the domain, but a part of these vortices are re-entering the domain, and it creates numerical issues usually. So then this type of boundary condition really help us. But what we concerning the inlet boundary conditions, there is multiple options what we can use, and let me introduce 3 options. So there is classical choice, which is just to prescribe some inlet profile at some profile at the inlet part of the boundary. This is one possibility, or what is also usually quite commonly used is to prescribe some pressure difference between the inlet part of boundary and the outlet or reference part of boundary, and this can be realized by the do nothing or directional do nothing boundary conditions just by choosing some constant value here at this position. Okay, and we wasn't completely satisfied with these 2 options, so we decided in the end also to choose and apply a different approach, which is basically this third possibility, which we refer as a weakly enforced velocity or penalization approach. And in this penalization approach, we again is based on the directional do nothing boundary condition as before, but we added here weakly enforced we weakly enforce the Dirichlet boundary conditions at the inlet part of the boundary. And this is enforced by 1 over epsilon, where epsilon are penalization parameters. Let's look at these figures. These are the results for the case when we have a prescribed motion of the boundary, and the boundary is really closing and opening again. And what happens at this very simple simulation? When we fix the inlet velocity here, referred as well, then the velocity at inlet part of boundary remains all the time the same, the black line. However, as the channel is closing, then the pressure really increase heavily. Yeah, and we get some very steep increase. Or we can call maybe explosion this part. So this is what we can really expect from this use of the incompressible model. But the values of the pressure are unphysically huge. So this is something we wouldn't like to obtain in our simulation. So if we use the second option, so we prescribe some difference in pressures between inlet and the outlet part of boundary, which is here referred to like the press, and shown by red line, we see that the pressure difference remains all the time the same. This is phi, almost a phi, but the inlet velocity really oscillates heavily. So this is usually what wasn't from our colleagues from the Institute of Thermomechanics. They say that this is not completely observed at their experiments, and they see some oscillations of the inlet velocity as well as pressure difference between inlet and outlet. And this mimics basically most precisely or in best way the penalization approach with suitably chosen penalization parameter, where we see some oscillation of inlet velocity, which at the part where the channel is open is not so huge, but are limited to given inlet profile. And we also, based on the chosen penalization parameter, we also can control the maximal pressure in our simulation. So therefore, we suggest to use this boundary condition in our simulation. Okay. So, and how the things are connected together, these two models, I would say in classical way. So what is a little bit unpleasant is that the location of interface is also one part of unknown, but it can be implicitly described by the as a reference state plus the unknown displacement at the given time t. By this implicit formula, we can find the location of the interface at every time step. And for the fluid flow program, we prescribe just that this Dirichlet boundary conditions, where this is the deformation domain velocity, the velocity of domain deformation, which are computed based on this AV mapping. And as I presented before, we have here also aerodynamic forces, which is prescribed to the elastic body in form of this Neumann boundary conditions, which has in the end this form. Okay, so that was the mathematical model, and now let's move to the numerical part. So for the numerical simulation, we use the finite element method. So we need to have a big formulation. So here we use this quite standard one. So the big formulation of linear elasticity problem look like this, where this E is the small strain tensor, and this formula we apply the finite elements of the first order, and this leads in the end to such system of ordinary differential equation of second order, where we get these finite element matrices, M for mass matrix, K for stiffness matrix, and C is some potential additional matrix related to that thing. And this system we solve in time by the Newmark, which is second order accurate and conserve energy. The fluid flow problem is again much more demanding. So first here we first discretize this problem in time. So we use vector differential formula of second order, and then we after this time discretization we apply we find the big formulation and solve which can be rewritten in such a way that we are looking for we would like to find a solution of this abstract problem where the form A is given on the second slide and on the next slide and should be equal to the functional f on the right hand side for any test function pair of this on this space. How look like this? What is the definition of this form A? You see that there's a terms related to time derivative. Then this convective term is a little bit changed because we applied 2 times the Green's theorem on this term in order to move the derivative also on the velocity itself, and by this second application of Green's formula we also get this nonlinear term where we split it and one part is absorbed by the boundary conditions, and this part where the plus means just the positive part of this bracket, which is just the normal velocity through these boundaries, and this really increase the stability of this positive. And then this is classical viscous part, pressure part, and the divergence-free constraint. And by red, you can see also that the implementation or the definition how is applied this penalization of inlet penalization boundary condition in this sense. And this is the right hand side for this. Okay, and then here you can see some details. But this is not enough completely because in this problem there are usually quite or middle one the Reynolds numbers, and we have to really overcome some stability issues connected with higher Reynolds number. So in this case we apply streamline upwind Petrov-Galerkin stabilization, and as well as the pressure stabilization and dip stabilization in order to really keep the host schemes stable. In the end, the linearization is in order to solve this, some system of linear equation. System of linear equation is done by this form, and we apply the P1 bubble, P1 finite elements, which fulfills Babushka-Beze stability conditions. Okay, and in the end, this whole scheme is we use the partition approach. So it means that each physical problem is solved by independent solver, and they have in loop to fulfill and make few iterations until the convergence criteria is found. So this take take us some time, and this is the way how we solve this problem. So first we solve the new displacement, and when we have new displacement, we can adapt the whole computation domain for the fluid flow. After the fluid flow, we compute the aerodynamic forces, and when we have the aerodynamic forces, then based on we use these aerodynamic forces as the criteria for convergence, and if they are all they don't change so much, then we can increase the time and continue with the next time step. If not, then we have to apply an additional inner loop of this. Okay. What we have also investigated was the influence of the how different realization of aerodynamic force computation influence the whole the results of this. And here we compare three approaches. So first one is to you see before that the aerodynamic forces is defined like the boundary integral over the pressure and some velocity gradient. And so first option is to compute directly this boundary integral, also using some extrapolation for the from the finite elements close to the boundary, which is where we lose some accuracy due to this extrapolation. Or the second options we suggest was to use a reconstruction of this velocity gradient, which is usually one order less than the used finite elements, and to really increase this by the reconstruction the degree of the polynomial degree of this approximation. And this we done by the classical babushka recipe. So when we need to compute some value at the point A, we build first a patch of elements around this point A, and based on then we use the values of gradients at the center of each triangle from this patch, and based on these values, we use the least square method. We find some reconstructed value in order to evaluate this pressure gradient. This approach for sufficiently for meshes with sufficiently high accuracy really increase this one. And the third method we compared was also to use a weak reformulation of this aerodynamic forces. So when we have a body which is here described by the domain omega s, and we have a flow problem in domain omega f, depending on time, then we can from the around this structure domain, we can define one layer of finite elements denoted like the omega strip, and inside this domain you can define a function which is value on the interface and slowly decreasing to zero outside of this interface. And then if we test the equation from the of the momentum conservation by such a function, then we can after the application of Green theorem, we can reformulate this in this formula, where we can see that on the left hand side on the left hand side there is basically the aerodynamic forces tested by this test function associated with the interface, and on the right hand side we will get really just the volume integrals without need to differentiate our velocity function, which are approximated by some given polynomial value, and this is really in this formulation we doesn't lose accuracy according to this, and we prove it or we show it on the some numerical example. I have some results also at the appendix. Okay, so doesn't matter. Let's show me you the first video of this computation, and this video I hope. Let's. Okay, I'm sorry. I hope I thought I downloaded this, but I don't see it here. Okay, so let me try to show it to you here. So if this is the computation of this with this vocal folds, where there are some prescribed inlet velocity by this penalization boundary condition, and as you see, these vocal folds starts to vibrate, and this vibration is actually is exponentially increasing, and this is additional characteristic of the human vocal folds, that this vibration when you start to speak, that okay, that the start of the phonation is really happening in the at the regime of the flutter instability, where the inlet velocity really, when the inlet velocity exceeds the critical value for the giving the stability of this vibration. And if you look at these graphs, then if here is shown one the top point from one vocal fold, and if we look at the time behavior of this vibration, we really see that these are in time exponentially increasing. Also, if we plot just this as in coordinates x, y, then we see that this how this motion evolves in time, and the similar can be seen also in by means of the gap between the both vocal folds. When by black line you can see the reference value and how the gap is really starting to be exponentially decreasing here, and also the pressure value is becoming starting to really increasing, how these vocal folds starting to close the channel between these. And here, if we compute the structure velocity, the energy of the structure part, we also see that that there is an exponential increase in the structure energy. And this is something, as I mentioned, typical for this vocal folds, because this really happens in nature, and the fact that this is instability doesn't represent some big issue is that at some point there is this exponentially increasing displacement is restricted by the mutual contact of these vocal folds. And this is, however, also very difficult to capture numerically at our scheme, this contact. So this in this setting, we were only able to compute the motion up to some certain point when the computational fluid for mesh was too much deformed, and then we are looking for some approach how to compute further this. Okay, so this was the fluid structure part, and now let me focus on the aeroacoustic part. So basically, we can the acoustic pressure as a representative quantity of this problem is usually very small compared to the fluid to pressures usually found in the fluid flow problem. And this creates many problems, and it is usually much more better than to use the compressible Navier-Stokes equation, to use some different alternative to this approach. And one alternative is to use some perturbation approach, which is usually called like the acoustic analogies, to deal with this. And by application of this, we have certain benefits. So this benefit is that we have usually some better adjusted scheme where we really don't have to be so much careful about the resolution in time and space of all phenomena inside. We are just looking for the acoustic phenomena, and what we lose is that we lose some potential influence of the acoustic field back to the fluid flow problem. But this is what we assume at the beginning is not a big issue here. So as I mentioned already, why is this to use some hybrid approach, some acoustic analogy? A good idea is that we really would like to solve very tiny part of the overall pressure, and we have also big disparities and the lengths and velocities where the typical length of the of our fluid structure is rather millimeters or something like or similar, where the acoustic typical length scales for acoustics are rather meters. Yeah, and also the pressure disparity then. And then what is also could be a big issue is to have a to choose the correct boundary conditions for example, open domain problems and so on. So here also this hybrid approach suggests some better options. So let me introduce here two models for this acoustic analogies. One is the Lighthill analogy, and this is the basic setting is such that we have some domain where there is a fluid flow with quite big gradients and significant velocities, and as the flow moves around this obstacle, it creates sounds, and this sound is further propagated also to those bigger domain. We call it aeroacoustic domain, where the fluid is more or less in the rest. And how to describe these two situations? So both of these situations are described by the Navier-Stokes equation, and we can. If we look at this Navier-Stokes equation, we can take the conservation of momentum and rewrite a lot of things as a divergence of so-called Lighthill tensor. Lighthill tensor is given here, and we keep on the left just the time derivative of the rho times velocity component, and here we have a we add here at this part also the divergence of this density fluctuation, what we also add to the right hand side. And we take also the classical continuity equation, and then if we apply on the upper equation the once more the divergence, and on on the continuity equation the time derivative, then we end up with term on the left hand side, which is basically the wave operator. And this wave operator can be by assuming this relationship between pressure and the density, the isentropic relation can be formulated in pressures or in velocity fluctuation. And what remains on the right hand side is basically this Lighthill tensor. So then we have a divergence of the Lighthill tensor. And this is first one of the first approaches how to really model the propagation and the generation of the sound created by some flow around bodies. Like to say, okay. And if we look more carefully about what we have on the right hand side, what I would like to mention here was that this Lighthill tensor is assumed to be non-zero only in the fluid domain, and when we are at the bigger domain, we have basically we assume that there is no sound sources as the velocity is here 0, then also this Lighthill tensor is 0, and we have just the propagation related to this wave operator here. Okay, and how look like this Lighthill tensor? We can identify a multiple mechanical mechanism how the sound is produced. So first we have here raw times tensor VU Vj Vi Vj, and this is connected with the flow motion. Then we have this part which is basically non-zero only for the case when we have some non-zero entropy in this in the studied fluid flow problem, and then we have also viscous part. And usually for our case, when we have a flow Mach number where we assume further the isentropic process, we can simplify this Lighthill tensor and approximate it like some reference with density times this velocity tensor. Okay, so what is nice about this Lighthill analogy is that the approximation is used only the structure of the Lighthill tensor in the end of the derivation of this analogy. And if we would keep here also some pressure fluctuation on or the density fluctuation, we would also include in the problem also the acoustic nonlinearity, the some convection due to some background flow and reflection or attenuation of the acoustic waves, and that we also do the approximation in the end. It allows us to also arrange this model to different situations based on these right-hand side sources. What is not so nice is that in general we are solving just for the pressure fluctuation and not directly the acoustic pressure, which is a different value than the pressure fluctuation, because the pressure fluctuation can be seen as a superposition of some hydrodynamic pressure connected with the motion of vortices, plus some acoustic pressure, which is usually very of much smaller magnitude. And from the numerical point of view, we also need to, in this case, post-process second derivative of this term. And this derivative is space derivative, which brings necessity to have a higher resolution scheme in order not to lose some too much accuracy. Okay, so here is some very simple sketch taken from the book of Professor Kaltenbacher, where he used some where he first simulated von Karman's streak behind this cylinder, as you can see here, this typical vortices of flow. And when he apply on this fluid flow the Light-Hell analogy, so he really compute this sound source based on this velocity approximation, then he gets some such kind of pictures. You can see here the waves which are really propagating out of this domain, but you can see also at the domain close to the cylinder this heavy oscillation which is really connected with these vortices of von Karman street. We cannot say that these vortices are the acoustic one. Okay, so therefore there is another approach, or the whole family of another approach, which was first introduced by Hardin and Pope in '94, and further reformulated by Evert and Schroeder in 2003, and in the end a little bit more polished by a team of Professor Kaltenbach. And this approach is connected with that thing that we would like to really solve directly for the acoustic pressure. So we would like to make a more insightful decomposition of this float velocity. So instead of decomposing the float velocities in the mean and some fluctuation one, we decompose it. We use a further decomposition of this fluctuation part in the fluctuation connected with the incompressible pressure and the acoustic fluctuation. And the same we also perform for the pressure and for the velocity, where we cannot say that there is some fluctuation for the velocity of the density in the incompressible Bono, but this is something we have to use some correction rather than just the fluctuation. Okay, and if you really use the thing that these three assumptions, that the acoustic field is really heavily fluctuating in time, and that we assume that the acoustic velocity is irrotational, and that the acoustic velocity is different for the pressure fluctuation, then if we apply these assumptions in Navier-Stokes equation, we neglect all nonlinear terms and further some additional terms connected with viscosity and etc. We end up with such set of perturbation equations, which where the unknowns are acoustic pressure and the acoustic velocity. We assume that we know also the mean velocity, and that on the right hand side there is in form of sound sources are the time derivative of the incompressible the pressure fluctuation connected with the incompressible pressure and this convective part of them. Okay. So these are more difficult to solve than the wave equation, but in the end, and there are actually 4 of them, because we have 1 unknown in pressure and 3 unknowns in velocity. But if we observe that the acoustic velocity can be related to the acoustic potential by this formula, then the previous equations can be reformulated just in this form, which almost resemble the wave equation, where instead of the classical time derivative, we have here a substantial derivative, where this substantial derivative is actually what can we see here on the right hand side, that we in this equation we also introduce the influence of the background flow on this acoustic propagation. However, if we omit here this influence of this background flow on this acoustic propagation, which is also quite reasonable approach for low Mach numbers, we end up with this aeroacoustic wave equation, where we have on the left hand side again the wave operator related to or taking as an unknown acoustic pressure, and on the right hand side we end up with just the second time derivative of this incompressible pressure component. So this is our model, second model we are concerning. And if we use the same situation with the cylinder as before and look at the acoustic pressure, solution in acoustic pressure, in the end we will see such a waves and no huge hydrodynamic fluctuation related to the vortices behind this cylinder. So, and in general, this perturbation approach is more difficult to derive, because you have to know what approximation has been done during the way, and but on the other hand, it has a benefit of being a variable directly for the acoustic pressure, and that you need to save during the computation only the scalar values or pressure values, and only in the differentiation is made in time, which also is has better numerical properties related to the space derivation. Okay, let me show you the second video where there's a different computation of this. No, about this, about this motion, and based on there was some older one, but based on this older one, I then I perform the aeroacoustic computation. So here, how the aeroacoustic computation is done, basically, I compute the aeroacoustic sources, and this they are computed only in the domain where the fluid flow problem is solved. So it is somewhere near to the vocal folds. And then I use a different acoustic mesh, and I interpolate, and the mesh is refer to this bigger domain. Then I also include the vocal tract, because this is important for to obtain a different that the acoustic problem can be modified by different resonant frequencies of this vocal tract. And I interpolate, because this acoustic mesh is different from the fluid flow at this part, I interpolate the values on the acoustic part, and then I perform the time simulation, how these sources from this part propagates through the neck and outside of the mount in this model. And because here outside of the mount should be the open boundary, and the waves should go out of these, then this is also quite tricky to simulate numerically. And in this case, I use a perfectly matched layer, which allows to really let the waves go out without any reflection from this boundary. And these are the sketch how look like these the sound sources in the in the Lighthill analogy. So you can see that this is the divergence of this velocity tensor. So this is rather connected with the boundaries of the strong jet going through this vocal folds and this channel. And in the case of this acoustic wave equation, then we have a second time derivative which is rather connected with the centers of vortices behind. And once we have computed all the some sources in whole in longer for the whole longer time, we have many time signals at each point of this domain, and then we can also perform a Fourier transformation on this, and based on this Fourier transformation, we can look what happens at different frequencies. So if you look at the frequencies 230 Hertz, then which is at this simulation connected with the motion of the vocal folds, we see that in the Lighthill case, there is a strong sources around the interface and closely behind this, and that the some sources are also inside this channel at this frequency. And if we increase this, the frequencies, you will see also some bigger values at these quite big frequency of 2050 Hertz. But these frequencies, you don't see that the sound source is located inside this vocal folds, but rather outside, which is connected more with some turbulence-like structures of the fluid. And this is the acoustic computation domain, which should resemble the wobble U. And if I put the microphone or the sensor at the end of this vocal tract shape and store the signal of this time simulation in the end, and perform at this location the Fourier transform, I will obtain such a frequency spectra for this sound. And you can see that for the first presented acoustic analogy called Lighthill one is quite overestimated at these regions, and this is we expected it due to the character of this pressure fluctuations rather than the acoustic pressure. And the second two I present here, this acoustic wave equation is rather has quite reasonable behavior in this case. What is in this case this capital F here, F1, F2, F3, and F4, these are the resonant frequencies of this vocal tract. So it really likes that once you have some source at the given frequency at your vocal folds, then if this sound should propagate through the neck, it really suppress and increase the sound pressure level at these frequencies, and at the frequencies between they are rather suppressed or not so amplified. So you can see that these two resonant frequencies are highly amplified, and also the fourth one and the third one. I'm afraid that the third one was rather some numerical effect related to the to the model of this outside part of the boundary, but in this case it wasn't too much amplified here in this case. So I think I speak already 1 hour, so I don't know if you would like to have a longer time also or not. Okay, so I have in the end I have a more recent work where we would like to address the problem with this contact modeling, and this is complicated due to many cases. It is first of all it happens some topology change in this domain, and this is also very complicated in our airy framework connected with the finite elements. And once this is one problem, and we have also deal with the detection where the contact is happening, and also this impact forces is usually quite large and has a very rapid dynamic. And also we have to we would like to include in our. So here we have. So let's address the modification which we need, which is needed to take in our scheme to somehow model the contact. So first one, you have to somehow introduce the contact forces and the model for contact in the elastic part. So here we use the Hertz impact forces, rather very simplified method where the impact forces is related to some penetration depth, delta, and this is rather the penalization. This is also in literature called the penalization approach, so where the elastic, where the impact forces is related to some penetration depth and with some penalization factor or some coefficient. Okay. This is not so difficult, but more difficult is to also address the fluid flow problem, and that there is a huge increase of the pressure once the channel is closing. And as I introduced before, this can be somehow modeled in, or we can describe this behavior quite well, or with reasonable work by this penalization boundary condition, where if we choose sufficiently large small disk penalization parameter. So afterwards, based on this penalization parameter, we are able to control the maximal pressure during our computation, especially when the channel is closed. But in the end, we also somehow need to check to deal with the topological change, and this and in this case we decide to define some minimal gap which has to remain all the time in this situation in the computation in this domain. So if we assume just symmetrical problem, then this gap threshold will be denoted like this, and we don't allow to deform the fluid flow mesh more than this gap. And what happens with the structure mesh at the point where the top of the vocal folds overcomes this gap threshold, we somehow decouple the structure and the fluid part, and allow the structure part to move further up to it penetrates to the second vocal folds, and based on this penetration, very small penetration, we compute the impact forces which further after some times move the vocal folds down. And during this time, we have in the fluid flow domain, we have still this very tiny gap, which is really, which can be made very small. And in order to really suppress all flow from the left to the right hand side through this channel, which should be closed, we additionally introduce an additional term in the Navier-Stokes equation, which can be seen as a artificial porosity term, where this where we have some coefficient alpha and this characteristic function related to this red part of the domain. And this red part of the domain is active only when the channel is closed, and then it disappears. Yeah, and using this setting, we were able to. Okay, I will show you to mimic this. Okay, to Okay. To mimic the contact behavior. So in this situation, we keep the top vocal folds static and just apply some prescribed motion on the bottom one. But you can see that at a certain point there is apply this minimal gap threshold, and the channel remains open. However, at this situation there is no flow through this channel. So this is our new approach to this contact problem, and seems it works quite good. Okay, and now there are just some tests. What happens if we apply a different gap threshold? You can see here the motion of the gap measured between the vocal folds, and that we here apply different thresholds, and that the pressure drop and inlet velocity remains almost the same for different gap thresholds. However, if we apply a different penalization parameters given in this table, we see that we get a really different results in the inlet velocity, so in the pressure drop. So that's let me conclude. So I present you some fluid structure acoustic interaction problem. I also try to describe the benefits of the hybrid approach when you use some acoustic analogies instead of solving the complete fully compressible Navier-Stokes equation, and I show you some results. So thank you for